Have you ever wondered why everything in the universe keeps spinning without rest, and yet we feel completely still? The Earth spins at more than 1,000 miles an hour. At the same time, it moves around the Sun at a distance of as much as 93 million miles. Meanwhile, the entire solar system is rushing through the galaxy at nearly 500,000 miles in a single hour. And still, we do not feel even the slightest tremor. Our heartbeat does not shake. Our breathing does not falter. Everything feels as if it were frozen inside a universe that never stops moving. But what if that stillness is the greatest illusion of all? What if time itself is only the echo of an even deeper rotation? A rotation that began before the atom, before light, before memory. Tonight, we are going to let ourselves drift into that mystery, not only to ask why everything moves, but also why it seems that nothing can ever truly stop moving. So close your eyes, let the sound of the universe hum beneath your skin, and come with me into the turning heart of all things. And before we begin, if you feel generous, a gentle like or a quiet tap on the subscribe button would mean the world to me. It may be a small gesture, but I receive it with deep gratitude, because every bit of your support helps this little universe keep going and reminds me that these quiet stories still find their way to kind hearts like yours. Now, let's begin with the first question. Part 1. If everything in the universe is spinning, why do we feel as if we are frozen in time? The Earth is spinning at more than 1,000 miles an hour right beneath your feet, while also racing around the Sun at nearly 67,000 miles an hour. And in this very moment, as you take a breath, the entire solar system is also moving around the Milky Way at nearly 490,000 miles an hour. And yet somehow we feel nothing. The coffee in your cup does not ripple, the air is not swept away, and the stars still seem motionless. It is one of the greatest illusions of existence, a paradox between motion and stillness. From the tiniest electron to the largest galaxy cluster, everything in the universe is in motion. Atoms spin, planets rotate, galaxies curl into giant spirals of light and dust. Even the universe itself, according to some cosmological models, may carry a subtle overall rotation engraved into its structure. But if everything is moving, why do we feel motionless? The answer begins with inertia, one of the quietest and most powerful principles in physics. Isaac Newton first described it in the 17th century. An object in motion remains in motion unless an external force acts upon it. That law is the key to why we do not feel the endless rotation of the Earth. We are moving with the Earth, not apart from it. Your body, the air around you, the oceans, the mountains, everything is turning together in one silent rhythm. To feel motion, you need contrast, a push, a pull, a change. But here, there is no such thing. The Earth's rotation is stable, gentle, and ancient. It is the same now as it was when the first human beings lifted their eyes to the stars. Astronauts in orbit experience this illusion on a larger scale. When they are in orbit, they are traveling at about 17,500 miles an hour, encircling the planet in just 90 minutes. And yet inside the spacecraft, everything feels calm. There is no drag, no air friction, and movement takes on the appearance of stillness. This phenomenon has a name: uniform motion. It is the same principle that lets you sip tea on an airplane flying at 500 miles an hour. You and the plane are moving together. Only when turbulence appears, when a sudden change breaks that uniformity, do you feel motion. The Earth's rotation is just that smooth, with no shaking, no friction, and no sudden shift. And because space is almost a perfect vacuum, nothing reminds us that we are moving at the speed of the cosmos. Neil deGrasse Tyson once said that we are sitting on a rock in space orbiting a star, while that star orbits a galaxy moving through the universe, and we call it home. It is easy to forget that because our senses were never designed to handle scales like these. The inner ear, the part of the body that senses motion and balance, evolved to deal with walking, running, and climbing, not the rotation of a planet thousands of miles wide. It responds to acceleration, not to constant velocity. That is why you feel the moment a car begins to move, but not its steady motion once it is already going. On Earth, everything is moving with you. There is no beginning and no end, only a permanent drifting onward. And yet scientists can still measure this hidden motion with astonishing precision. The Foucault pendulum, first demonstrated in 1851 by Léon Foucault, swings freely while the ground beneath it slowly turns away. It does not need the stars to prove that the Earth rotates. Its slow shift over the hours is a visible image of the planet's quiet spin. If you have ever stood before such a pendulum in a museum, then you have watched time and motion merge in every gentle swing. On a cosmic scale, that rotation is far from trivial. It gives us day and night, stabilizes the planet's magnetic field, and protects us from the radiation of the sun. Without it, one side of our world would burn, while the other would freeze. NASA's Goddard Space Flight Center says that the Earth's rotation has slowed slightly over billions of years, largely because of the tidal pull of the Moon, making the day longer by about 1,7 millisegundos per century. So even inside our stillness, there is a slow and invisible change. But when we look deeper, we see that rotation is not only an earthly phenomenon, it is a mark left on the whole universe. Stars form from collapsing clouds of gas and dust, and as they contract, they spin faster according to the law of conservation of angular momentum. Just like a figure skater spins faster when pulling in her arms, every planet inherits that momentum. The Earth's 24-hour cycle is a fossil from that ancient birth whirl. Even the sun rotates once every 27 days, dragging its magnetic field through space like shining threads. And the Milky Way, our galactic home, takes about 230 million years to complete one full turn, carrying hundreds of billions of stars in a spiral dance that began long before our planet ever appeared. The James Webb Space Telescope, or JWST, has captured galaxies so far away that their light has traveled for more than 13 billion years. And even those early galaxies already showed signs of rotation. Scientists from the European Space Agency found extremely subtle differences in their light. One side shifted slightly toward red, the other slightly toward blue. That is a clear sign of spinning motion. It seems as though the tendency to rotate was written directly into the DNA of the universe. But how can everything be spinning and still make us feel that all is truly still? Part of the answer lies in relativity. According to Einstein, there is no such thing as absolute motion, only motion relative to something else. So from our frame of reference here on Earth, we are standing still, and it is the universe that appears to move. From another frame of reference, the opposite is true. That symmetry is what keeps physics consistent and makes our sense of stillness only an illusion of perspective. In deep space, astronauts aboard the International Space Station circle the Earth at nearly 5 miles per second. But what they experience is weightlessness, not motion. Their sense of down changes every 90 minutes, yet the mind adapts. We too are travelers in motion who have simply adapted to stillness. That stillness is a survival mechanism, a balance between the limits of our senses and the demands of the universe. If somehow we could directly feel the Earth's rotation, the pull of the sun, or the drift of the galaxy, our perception of time itself might shatter. Because motion and time are bound together. When rotation defines day and year, it also defines the heartbeat of the universe. Carl Sagan once said that time is woven into the very fabric of the universe, and we are part of that thread. The stillness you feel right now is not the absence of movement. It is the harmony of everything moving together. So when you lie down tonight beneath the invisible shifting of the stars, remember this: you are not standing still. You are flowing in a gentle cosmic river, continuous and endless. Every quiet moment is only the universe moving too smoothly for you to notice. And in that perfect balance between motion and stillness life finds its peaceful rhythm. Take a slow breath. You are still spinning, and you always have been. And the silence you hear is the sound of everything moving together. And as we go deeper into this story, let us turn back toward the past, toward the moment before motion began. When the universe made its very first turn of its own, that is where the next chapter opens. Part 2. Who created the original motion of the universe? If you could rewind time, not by a few centuries, not even by a few millennia, but all the way back to the very first second after the Big Bang, what would you see? Would there be light? Would there be sound? Or only a sudden motion, a whirl, a twist, a first turn of everything that would ever exist? The question of who or what created the universe's first motion is not only philosophical, it is also physics. It lies deep within the equations of cosmology, in those first moments when matter, energy, and space itself were just beginning to take form. Astronomers call that the Planck era, an extremely early interval around días a la menos 43 segundos after the Big Bang, where our current laws of physics can no longer fully describe reality. But what we can infer suggests something extraordinary. The universe may not have been born in stillness, but in a very slight rotational motion. Today, scientists study the cosmic microwave background radiation, the faint light left over from the Big Bang, recorded by satellites such as WMAP and Planck, and they have found tiny anomalies, temperature ripples differing by only a few parts per million. Those patterns tell us that the early universe was not perfectly uniform. There were slight differences, and from those tiny differences grew everything we see today: galaxies, stars, planets, and life itself. But some researchers noticed something even stranger: a faint alignment, a large-scale twist in the way those ripples were distributed. They called it the axis of evil, a mysterious pattern suggesting that the universe, on the largest scales, may have a preferred direction of rotation. According to data from NASA's WMAP mission and later observations from ESA's Planck satellite, that alignment could either be a subtle artifact of measurement or evidence that the whole universe once rotated. If that is true, that rotation may have shaped everything from the spiral arms of galaxies to the very arrow of time. So how could such a rotation have begun? The key may lie in quantum fluctuations, tiny energy variations that occurred when the universe was smaller than an atom. Even in perfect emptiness, such fluctuations happen naturally. As NASA's Goddard Center has emphasized, quantum fields are never perfectly still. They are always vibrating. When the Big Bang occurred, those vibrations were stretched and amplified by cosmic inflation, a brief but explosive phase of expansion that made the universe grow faster than the speed of light. That violent expansion may have turned some of those quantum fluctuations into swirling motion. Inflation theory, first proposed by Alan Guth in 1981, explains why the universe looks so uniform and yet still contains the seeds of structure. But in recent years, data from Planck and BICEP2 has also suggested that during inflation, subtle rotational modes called B-modes may have existed in primordial gravitational waves. Those tiny twists in space-time may be fossils of the universe's first spin. They suggest that the Big Bang was not just a simple explosion, but a turbulent birth that stamped rotation into every level of matter. And that makes sense when we look at what happened next. As the universe expanded and cooled, matter began to gather. First quarks and gluons, then protons and neutrons, and then atoms. Each of them carried a small amount of angular momentum. When gravity later pulled them together into gas clouds and galaxies, that ancient angular momentum was preserved. It is the same principle that makes a figure skater spin faster when pulling in their arms. In physics, nothing spins naturally if there was no motion before it. So that first turn, however small, must have existed from the beginning. Today, astronomers can still see traces of it in distant galaxies. In 2011, researchers from the Harvard-Smithsonian Center for Astrophysics analyzed more than 15,000 spiral galaxies and found a subtle preference in the direction they spin, an imbalance that may go back to the early universe. Even though no final conclusion has been reached, that handedness of the cosmos suggests our universe may not be completely random, but may instead carry a hidden rhythm, a quiet spin that everything still follows. Even dark matter, the invisible framework that holds galaxies together, may bear the mark of that twist. Simulations from NASA's Jet Propulsion Laboratory show dark matter halos twisting and rotating over billions of years, guiding the visible galaxies inside them like whirlpools carrying leaves. Without that rotation, galaxies might have torn themselves apart. It is as if the early universe set everything spinning, and even now, the echo of that motion keeps the stars in balance. But the question of origin still remains. Who or what started that spin? Many physicists lean toward a quiet answer: symmetry breaking. In the very first moments of time, the forces we now know as gravity, electromagnetism, and the nuclear forces were once unified as one. But as the universe cooled, they began to separate. And in that separation, tiny asymmetries, tiny defects appeared. According to ESA, it was those small departures from perfect symmetry that allowed structure, motion, and rotation to exist. Because in a perfectly balanced universe, nothing could move at all. Just the smallest break in symmetry was enough to give birth to motion. We see that principle everywhere. In the direction galaxies turn, in the way atoms spin, even in the left-handed tendency of neutrinos, as though nature itself was never completely symmetrical. That tiny imbalance is what allowed everything to move. Some scientists have even tried to test whether the whole universe is still rotating. In 2020, astrophysicist Leo Shamir of the University of Kansas analyzed more than 200,000 galaxies from the Sloan Digital Sky Survey. He found that galaxies on one half of the sky tended to rotate more in one direction than the other, hinting at a large-scale twist in the cosmos. As Shamir wrote, the universe may carry a collective pattern of motion, a preferred direction born in the early universe. This does not mean that the universe spins like a giant top. Rather, it may mean that the structure of space-time itself once had a slight twist during expansion. Even an extremely subtle twist could spread across billions of light-years. To us, it may appear invisible, but on cosmic scales, it could shape the geometry of everything. To test these ideas, NASA and ESA continue mapping the universe in ever greater detail. James Webb has captured light from galaxies that formed only 300 million years after the Big Bang. Some of those ancient systems already showed organized spiral patterns far too early to be explained by chance alone. That means the seeds of rotation were planted almost immediately. The universe did not need to learn how to spin. It was born spinning. Even at the quantum level, rotation is fundamental. Every particle, from electrons to protons to neutrons, carries intrinsic angular momentum, a basic property of matter described by quantum mechanics. It is not a literal physical spin in the way we usually imagine, but a deeper mathematical turning encoded in the wave function itself. Richard Feynman once said that spin is one of the deepest properties of nature. A particle is not actually spinning like a little object. It simply has spin, just as it has mass. So in one sense, rotation was not something added later. It was part of the design of existence from the start. When you look up at the night sky, you are looking at the inheritance of that motion. Every galactic swirl, every planetary orbit, every photon of light, all of it flows from that first cosmic turn. Without it, matter would never have gathered, stars would never have formed, and time would never have found its rhythm. Motion is not an accident of the universe. It is the heartbeat of the universe. And although we may never know exactly what triggered that first turn, the evidence keeps whispering that it was always there. Quiet, steady, invisible, and yet carved into everything we can see. As one cosmologist once said, The universe keeps memory not in words, but in patterns of light. And inside those patterns lies the faint trace of the first motion, a twist older than time itself. So when we ask, who made the universe spin, the most honest answer may be this. The universe never had to learn to move. It was born in motion. Rotation was not created, it was inherited. Take a breath. The atoms in your body are still turning with that original impulse, from the smallest electron to the spiral of the Milky Way. That same turning has continued for nearly 13,8 billion years. We do not stand outside that motion. We are its continuation. And as we move forward in this story, we come to the next question, one that rises naturally from the last. If rotation helps shape the birth of the universe, could it also be the reason life exists? That is what we are about to explore next. Part 3. Can rotation make life possible? If the Earth did not rotate, the world would become unbearably extreme. There would be no day and night as we know them, no familiar rhythm of time, and the climate would be thrown completely out of balance. One half of the planet would sink into eternal ice, while the other half would be scorched beneath endless heat. A dead world drifting in light. But because this planet rotates, it seems almost to breathe. Every dawn, every wave, every gust of wind begins in the same ancient motion that started 4,5 billion years ago. The Earth's rotation is not just a movement, it is a machine, a delicate balance that sustains everything we call life. From the magnetic field that shields us from cosmic radiation to the temperature cycles that nourish oceans and clouds, the Earth's spin shapes this world in ways both visible and invisible. According to NASA's Goddard Space Flight Center, the speed of our planet's rotation near the equator is about 1,037 miles an hour, completing one full turn in 23 hours, 56 minutes, and 4 seconds, what scientists call a sidereal day. That steady rhythm sets the tempo for every biological and environmental cycle on Earth. Plants, animals, ocean currents, everything is synchronized to it. An invisible pendulum clock is ticking beneath all living things. The first consequence of the Earth's rotation is the alternation of day and night. It spreads sunlight across the surface, creating temperature differences that drive winds, currents, and weather. Without that daily turning, one hemisphere would remain trapped in eternal daylight and burn, while the other would freeze in endless darkness. Between them would stand a wall of violent storms, a twilight zone where life would struggle to survive. But because the Earth spins, the sun rises and sets, and energy is distributed evenly enough to create a stable climate and habitable regions. Rotation also affects the Earth's magnetic field, one of life's most important shields. Deep beneath our feet, the liquid iron core of the planet moves and churns, generating a natural electromagnetic dynamo. NASA explains that the Earth's magnetic field is produced by the motion of molten iron within the core, and that field deflects the solar wind, the constant stream of charged particles pouring from our central star. Without it, those particles could strip away the atmosphere, just as happened on Mars. The red planet rotates once every 24,6 hours, fairly close to Earth, but its smaller core has cooled and no longer moves in the same molten way. Without an active magnetic field, its atmosphere has gradually been swept away by the solar wind, leaving behind a dry, frozen desert. On Earth, the magnetic field also creates the auroras, those soft ribbons of light near the poles. They are not only beautiful, they are proof of protection, where lines of magnetic force curve and interact with charged particles from the sun. That light is like a reminder that the Earth's rotation is still generating an invisible force around us. The effects of rotation do not stop with sunlight or magnetic shielding. They also govern the atmosphere itself. Because the Earth spins, air moving from the equator toward the poles is deflected by what is called the Coriolis effect. That effect creates the great swirling wind systems and ocean currents that shape global weather. It is why storms form, why jet streams exist, and why warm and cold water are carried around the planet. Without the Coriolis effect, weather would become chaotic, storms would not develop the way they do, and climate would struggle to remain balanced. In fact, a planet's rotational speed directly shapes its climate. NASA simulations of exoplanets rotating slower or faster show that slow rotation can leave one side too hot and the other frozen, while excessively fast rotation can produce violent winds and shorter days that disrupt atmospheric stability. The Earth's 24-hour rhythm is almost ideal, long enough to distribute energy evenly, but short enough to prevent overheating. The length of the day also affects biology. Living things have evolved internal clocks, circadian rhythms, tuned to the planet's rotation. According to biological research, every living cell on Earth carries a molecular timekeeping system synchronized with that 24-hour cycle. It determines when leaves open, when birds migrate, and when humans sleep. If the Earth stopped rotating, that biological harmony would collapse. Day and night would no longer alternate in a steady way, and life as we know it would struggle to adapt. Rotation also helps shape the relationship between the Earth and the Moon. Billions of years ago, a Mars-sized object named Theia collided with the young Earth. That impact flung matter into orbit, which later gathered into the Moon. It also made the Earth spin much faster. Over time, the Moon's gravity slowed that spin down, stretching the length of the day from about 6 hours to the 24-hour cycle we know now. At the same time, tidal forces between the two bodies keep the Earth's axis relatively stable, preventing extreme climate swings. Modern astronomical observations show that such stability is essential for long-term habitability. Planets that wobble too much often endure devastating climate disasters. The Earth and Moon now exist in a gentle gravitational embrace, and the tides that shape our oceans are still quietly slowing the planet's rotation, adding about 1,7 millisegundos to the day every century. It is a reminder that even the heartbeat of this world is changing, little by little, too slowly for human eyes to notice. If we look beyond our planet, we see that rotation plays a similar role on other worlds. Jupiter spins once in just about 9 hours and 56 minutes, making it the fastest spinning planet in the solar system. That speed creates immense winds and terrifying storms, including the Great Red Spot, a storm larger than the Earth that has lasted for centuries. There, rotation creates both chaos and stability, distributing heat and shaping the planet's striped beauty. By contrast, Venus spins backward and extremely slowly, taking as long as 243 Earth days to complete one turn, and it has almost no meaningful magnetic field. Its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system. The contrast is astonishing. Rotate too fast, and storms dominate. Rotate too slowly, and protection disappears. Even Mars, whose day is only about 40 minutes longer than Earth's, shows what happens when the inner motion of a planet weakens. Once its core cooled, its magnetic field vanished, allowing solar radiation to gradually strip away its air and water. The weak magnetic traces left in its crust are only faint remnants of a once active world. Rotation is not an optional ingredient for habitability. It is a foundation. Observations of exoplanets suggest that worlds with clear rotation or atmospheric circulation often show better chemical balance and more even temperature distribution. Without turning, energy would either build up too much or escape too unevenly, creating unstable environments. NASA's exoplanet research program makes this clear. Rotation plays a crucial role in determining the climate and habitability of a planet. It may also be tied to magnetic protection on distant worlds. Some studies suggest that rapidly rotating exoplanets tend to keep molten metallic cores active for longer, which extends the life of their magnetic fields. Those magnetic fields then shield the atmosphere, increasing the chances that liquid water may survive on the surface, one of the essential ingredients for life. So when we ask whether rotation can make life possible, the evidence seems to say yes. Rotation shapes everything, from the length of the day to temperature gradients, atmosphere, weather, and safety from radiation. Life does not flourish in spite of motion. It flourishes because of motion. The speed of our world's rotation may have changed over the ages, but its influence still echoes through time. It guides the rhythm of the tides, the growth of forests, the migrations of animals. It defines our idea of time, not as an abstract thought, but as the physical turning of the planet beneath our feet. Neil deGrasse Tyson once said that we are not just in the universe, we are part of it. The Earth turns, and so do we. Take a moment to listen to that motion. Every rotation carries the whisper of 4.5 billion years of balance and movement. If the Earth stopped turning tomorrow, the oceans would rush toward the poles, the atmosphere would collapse into chaos, and the planet would stop breathing. But tonight, as it still turns silently beneath you, everything continues to function perfectly, quietly, continuously. So it is not too much to say that the Earth's rotation is the silent architect of life. The cosmic motion that once swirled dust into a planet is now turning that planet into morning, into wind, into rain, and into you. And as we move deeper into this journey, let us follow that turning farther outward, to where rotation no longer only shapes life, but begins to bend something even stranger. Because beyond a certain threshold, rotation does not merely move matter, it can begin to twist time itself. And that is where the next chapter begins. Part 4. Can rotation bend time itself? When rotation reaches its limit, it is no longer only motion. It becomes distortion. At extreme speeds, rotating objects no longer simply move through space. They begin to drag time along with them. Einstein's general theory of relativity, published in 1915, predicted that gravity and motion cannot be separated. They are two expressions of the same reality, the way mass bends spacetime. The greater the energy or angular momentum of an object, the more strongly the geometry around it becomes twisted. That twisting of spacetime created by a rotating body is called frame dragging, and it is one of the most subtle, beautiful, and well-tested predictions of modern physics. Imagine spacetime as the surface of a still lake. When a massive object spins, like the Earth or a black hole, it stirs that lake, creating whirlpools in the flow of reality itself. In those swirling regions, time itself can bend. NASA physicist Francis Everett, who led the Gravity Probe B experiment, once described it by saying that when the Earth spins, it drags the surrounding spacetime with it, like a spinning ball twisting honey. Gravity Probe B was launched in 2004 with 4 ultra-precise gyroscopes orbiting the Earth at about 400 miles altitude to measure that effect. After a year of observations, NASA confirmed that our planet's rotation warps spacetime by about 0.0011 degrees each year. That number may sound tiny, but it matched Einstein's equations with astonishing precision. Even this gentle world, turning once every 24 hours, can bend the flow of time. Now imagine an object spinning billions of times faster and sitting inside a gravitational field billions of times stronger. That is what happens near a neutron star. When a massive star dies, it collapses under its own gravity, compressing matter so tightly that protons and electrons merge into neutrons. The result is an object only about 12 miles wide, but more massive than the Sun. To conserve angular momentum, such stars can spin hundreds of times per second. Astronomers call some of them pulsars because their magnetic poles emit beams of radiation that sweep through space like cosmic lighthouses. As they spin, they generate the strongest magnetic fields ever known and bend spacetime so violently that even light struggles to follow a straight path. Modern observations show that time near a fast-spinning pulsar passes more slowly than it does on Earth. The stronger the spin, the slower the clock runs. According to Einstein, this is not magic. It is gravitational time dilation. Time passes more slowly where gravity is stronger or motion is faster. When you are near a massive rotating object, space-time itself gets pulled into its whirl. You cannot really remain still. You are dragged along as if the universe itself were circling around you. This effect becomes even more intense near Kerr black holes, rotating black holes named after mathematician Roy Kerr, who first solved Einstein's equations for that case in 1963. Unlike a non-rotating black hole, which simply pulls things inward, a Kerr black hole drags all of space-time around its axis. The closer you get to the event horizon, the more that twisting speed approaches the speed of light. Nothing, not even time, can escape that pull. The region outside the event horizon where frame dragging becomes unavoidable is called the ergosphere. In that region, nothing can remain still relative to distant space. Every particle, every photon, is forced to rotate with the black hole. It is as though space itself has turned into liquid, swirling in an enormous invisible vortex. X-ray observations around supermassive black holes show matter spiraling around them at speeds close to the limits predicted by relativity. In that spinning well, time behaves differently. If you could somehow hover safely near the event horizon, which for now remains impossible, your clock would run more slowly than clocks on Earth. Every minute you live there could correspond to hours in the rest of the universe. Einstein called this the bending of time, a direct consequence of motion and gravity working together. Images from the Event Horizon Telescope have shown that the bright ring around black holes is not light from the black hole itself, but from matter spinning around it. That light is bent and slowed by the curvature of space-time. Those glowing arcs are visual proof that rotation and gravity can bend not only light, but also the flow of time. The same laws appear on smaller scales too. Even satellites orbiting the Earth experience tiny differences in time. GPS systems must constantly correct for time dilation caused by both gravity and velocity. If those corrections were ignored, GPS clocks could drift by tens of microseconds each day, enough to create location errors of miles. So even here, where space-time seems calm, the bending of time is not just theory, it is part of daily life. When physicists simulate the regions near black holes, the mathematics becomes extraordinary. Rotation can twist space-time so strongly that closed, time-like curves appear, paths along which, in theory, a particle could return to an earlier moment. Whether such loops truly exist remains uncertain, but they arise naturally from Einstein's equations. In those extreme environments, the boundary between past and future loses its absolute meaning. Accretion disks around distant quasars, observed with modern infrared telescopes, show stretched and redshifted light, signs that time moves more slowly in those regions. Some of the light we detect today left those gigantic spinning engines more than 13 billion years ago. In other words, we are watching time itself stretch across the universe. It turns out that rotation does not only shape matter, it also determines how quickly time passes nearby. The faster the spin and the denser the object, the greater the warping of space-time. From our gentle planet to the violent centers of galaxies, the universe uses rotation to sculpt both motion and time. What we call the present is not the same everywhere. It depends on the speed and degree of twist in local space-time. Even light, which is usually considered the ultimate speed in the universe, is forced to bend and slow when it passes near massive rotating objects. X-ray echoes around black holes show that light can be trapped in the swirl for a short while before escaping. In those echoes, time stretches like a soft thread, measurable, predictable, yet endlessly strange. People have even wondered whether the universe itself, on the largest scales, might be bending time. A global cosmic rotation, however subtle, could influence how time flows across billions of light years. Current cosmological data does not show clear proof that the whole universe rotates, but the question is still open. Even the slightest twist on the largest scale could leave traces in the polarization of ancient light, clues that time itself might carry a preferred direction. The astrophysicist who served as the scientific co-author of Interstellar once explained that in deformed space-time near a rotating black hole, one person's future could become another person's past. Rotation does not only bend trajectories, it distorts the order of events, even the rhythm of existence itself. As strange as that sounds, these effects remain consistent and measurable. Time dilation around rotating objects has been verified with atomic clocks on airplanes, satellites, and mountain laboratories. The faster you move, or the deeper you are inside a gravitational field, the slower your time passes. That is not an illusion. It is how the universe preserves a perfect balance. So yes, rotation really can bend time. And even more fascinating is the reason that bending seems to obey a graceful, universal law, one that binds motion, gravity, and energy into one continuous whole. From Einstein's equations to every satellite still in operation, everything points to one truth. The universe does not merely move through time, it creates time through motion. Slow your breathing. Right now, your own time is tied to the gentle turning of the Earth and the swirl of the galaxy. You are surrounded by motion so precise that it writes every second you are living. And if rotation can bend time, then what happens when time itself begins to govern rotation? That is the mystery waiting in the next chapter. Part 5. If rotation controls time, then what controls rotation? Every second you live is shaped by motion. The ticking of a clock, the beat of an atomic clock, even the pulse in your chest, all depend on something turning. Electrons carry spin inside the atom. The Earth turns once every 24 hours, and as it turns, it drags space-time enough to change the way time passes. At the equator, where the surface of the Earth moves fastest, at about 1,037 miles an hour, clocks run just a little more slowly than clocks at the poles. That has nothing to do with temperature or air pressure. It is a consequence of relativity. Einstein showed that motion and gravity can stretch or compress time depending on how fast you move and how deep you are inside a gravitational field. So yes, spin does control time. But then the next question appears: who or what controls spin? To answer that, scientists turn to the most reliable timekeeping machines humanity has ever built: atomic clocks. Inside them, electrons move between fixed energy levels. When they jump from one level to another, they emit photons at an incredibly precise frequency. That frequency, in the cesium-133 atom, is what defines a second, which means that every second in your life is calibrated by a microscopic event tied to the quantum structure of matter. The turning of electrons inside the atom is a form of quantum spin, not a literal physical rotation as we usually imagine it, but a fundamental property of nature. In quantum mechanics, spin determines how a particle responds to a magnetic field, how particles bond together, and even how they obey the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state. So at the smallest scale, the measurement of time depends not on the turning of a planet, but on the intrinsic angular momentum of the particles themselves. But just as atomic spin governs time in the laboratory, the self-rotation of planets governs time on the cosmic scale. The Earth's rotation defines a day, while its orbit around the Sun defines a year. Yet those motions are not absolutely fixed. They drift. Tidal forces from the Moon continue to slow the Earth's rotation, adding about 1,7 millisegundos to the length of the day each century. To keep atomic time and planetary time from drifting too far apart, scientists occasionally add leap seconds, adjusting human clocks to match the planet's real turning. In a sense, we are always recalibrating our idea of time according to the Earth's rotation in the universe. If you compare clocks at different latitudes, The difference, though small, can be measured. A clock near the equator, where the Earth rotates faster, runs a little more slowly than a clock near the poles or high up in the mountains. Here, both special relativity and general relativity are at work. NASA explains that clocks at the equator run slower because they are moving faster and also sitting deeper in the Earth's gravitational potential. The difference is only a few nanoseconds each day, but it is real. The GPS system in your phone must constantly correct for those tiny effects. Each GPS satellite orbits the Earth at about 8,700 miles an hour, at an altitude of around 12,500 miles. In orbit, those satellites experience weaker gravity but move faster, which makes their atomic clocks drift each day. Without correction, the errors in position would build up very quickly. To maintain precision, engineers have to combine Einstein's equations with experimental measurements, meaning that, quite literally, they are correcting for the curvature of space-time caused by the Earth's rotation. So every time you open a map or receive a location signal, you are witnessing relativity at work, a silent coordination between gravity, motion, and spin. But who started that turning in the first place? Astronomers trace it back to angular momentum, a quantity that is conserved in physics. When the solar system formed 4,6 billion years ago, a cloud of gas and dust collapsed under gravity. As it contracted, it spun faster, just like a skater pulling their arms inward. That original motion distributed angular momentum to everything inside: the sun, the planets, the moons. Every body still carries part of that ancient spin. No outside force needs to keep them turning. Inertia is enough. In space, where friction is almost non-existent, a rotation can last for billions of years. So the answer to who controls self-rotation may well be no one. Once motion begins, the universe needs no extra hand to keep it going. But the link between spin and time becomes even stranger when we look deeper into matter. Rotation determines energy states at the atomic level, defines the day at the planetary level, and even drags time itself along. All of those layers are connected by one law: the conservation of angular momentum. Time, in that sense, is not a separate thing. It is a reflection of how energy and spin interact. Modern astronomical data shows that our Milky Way takes about 230 million years to complete one turn, carrying the sun and its planets in a vast spiral journey. The orbit of every star contributes to a galactic time machine. Just as atomic spin defines the second, the rotation of stars and galaxies defines cosmic eras. Even the sun rotates about once every 27 days at its equator, though not uniformly. Its poles turn more slowly, a phenomenon called differential rotation. That twisting motion generates the sun's magnetic field, which shapes solar storms and coronal mass ejections. When those magnetic storms reach Earth, they disturb our magnetic field and can even affect satellites and electrical grids. From the atomic scale to the scale of stars, rotation is never passive. It sculpts force fields that determine rhythms and interact with the very tools we use to measure time. Einstein's relativity ties all these patterns together beautifully. In his equations, the geometry of space-time depends on energy and momentum, including angular momentum. In other words, spin bends time. Remove spin, and space-time becomes simpler, flatter, less dynamic. Add rotational motion, and it begins to curve gently around planets and violently around black holes. In that sense, time itself is written in motion. The second is written by the quantum movement of the atom. The day is measured by the turning of a planet. Cosmic ages are measured by the rotation of galaxies. Everything that moves is measuring, and every measurement depends on motion. The early galaxies that humans observe at distances of more than 13 billion light-years already showed signs of rotation, meaning that angular momentum was present almost immediately after the beginning of the universe. That means the law linking spin and time has been operating since the earliest seconds. Spin is not a product of time. It is part of what makes the flow of time possible. So if spin governs time, and spin itself naturally arises from the conservation of motion, then who or what governs it? The most precise answer science can currently offer is this: the universe regulates itself. Every spin is balanced by another spin. Every slowing motion in one place is compensated by an exchange of momentum elsewhere. Even the smallest quantum particle follows the same equations, ensuring that angular momentum is preserved across all space and time. The laws of motion do not change. The universe runs on balance. What is lost in one place is made up in another. There is no central clock and no invisible hand winding it. Motion itself is what sustains time. So rotation is the universe's own internal gyroscope, the way it keeps everything in equilibrium. From the atoms in your body to the stars above your head, the same principle governs every scale of existence. Even when systems decay, collide, or slow down, their angular momentum continues to be passed on, keeping the cosmic clock ticking. And so, when you ask who controls motion, the universe may answer gently, no one. Motion sustains itself. That is the quiet balance beneath both time and existence. Take a breath. The atoms inside you are turning with the Earth, the Moon, and the Milky Way. You have always been part of that motion. Every heartbeat is only a small piece of a far greater rhythm. The universe began long before there were clocks, calendars, or even light itself. And as that rhythm continues, another question slowly rises, one that goes beyond motion itself and reaches toward the deepest structure of the universe. If the universe depends on perfect balance, what happens when that symmetry is broken? That is where we will go in the next parts. Your words, your presence, even your silence, they are like little stars guiding me forward, and I treasure them deeply. I will see you next time. May the universe turn gently around you. Leave your thoughts down in the comments below. If you enjoyed this video, don't hesitate to hit one like and subscribe to support us. Thank you.